This video will cover the assembly of a lightweight microdrive array with 21 independently adjustable screw-driven microdrives. Each microdrive controls the recording position of a single electrode. The microdrives are mounted in a computer-designed plastic base that stabilizes them relative to the skull of the moving animal and collects the electrodes into a densely packed pattern that can pass through a small craniotomy into the brain. The base also supports an electrode interface board for the connection to the recording instruments, which allows for the animal to be conveniently plugged in and unplugged at the beginning and end of an experiment. A plastic cone attached to the base protects the microdrives and electrodes from the elements in the rat cage.
Hi, I'm Fabian Grossman from the laboratory of Matt Wilson in the Picower Institute for Learning and Memory at the Massachusetts Institute of Technology. Today we will show you a protocol for how to fabricate one of those microdrive arrays. In our laboratory, we use those microdrive arrays to record from a large population of neurons in the brain of rats, for example from the cortex or hippocampus. First, we will show you how we designed our microdrive array. Then we will head over to the workshop where Steve and Stuart will show us how to process the raw materials and how to assemble them into a fully functional device. So let's get started.
The plastic base is designed using computer-aided design software and is manufactured using an inexpensive 3D printing process. We also model all the other components of the microdrive array. This allows us to carefully control the size and weight of the finished drive. At the top of the plastic base are two rings of holes that will accept the individual microdrives. The 3D model is sent to a service bureau that builds the design from a laser curable resin using stereolithography. This should only take a few days and the resulting part is lightweight and reusable. Once the part arrives from the service bureau, we need to prepare it for use. So let's head over to the workshop. The 3D printing process cannot reliably print small holes, so we specify smaller diameter holes in our models, then drill and tap the holes to the required size in the workshop. 3 different size drill bits are used to prepare the plastic base, a number 61-bit, a number 65-bit, and a 1.55mm bit. In the outer ring of the base, use a hand drill with a number 61-bit at very low speeds to prepare the pilot holes, where later the microdrive screws will be inserted. Next, prepare the holes for the microdrive support tubes in the inner ring of the base by drilling out these holes with a number 65-bit. Using the larger 1.55mm bit, drill out the holes that will attach the base to the electrode interface board and protective cone. To ensure smooth movement of the microdrive, insert a stainless steel sleeve into the inner ring of holes. Each sleeve should be press fit with a pair of pliers until it is flush with the top of the base. The screw pilot holes now need to be threaded. Use a pin vise to hold the tap and apply a dry lubricant before tapping. Align the tap and its hole by making sure it is parallel to a 23 gauge tube you temporarily insert into the neighboring sleeve. The holes that hold the interface board and the protective cone need to be threaded. Hand tap these holes the same way. The plastic base design features a tap starter for each screw pilot hole to make sure the initial threads are not damaged during the threading process. After all pilot holes are threaded, these tap starters can be easily snapped off using a razor blade. The electrodes are guided toward a single site at the bottom of the drive by a number of electroguide tubes. First, we need to make the collector cannula that will hold all the electroguide tubes. The collector cannula is made from a 1.5 cm long piece of stainless steel tube. The collector cannula will be held in with dental cement, so to enhance adhesion, carefully roughen the tube using a Dremel grinding wheel. Insert this cannula into the bottom of the plastic base. Position it so that 5 to 7 millimeters of the cannula remains outside of the microdrive array to facilitate surgical implantation. Attach the collector cannula to the bottom of the plastic base with dental acrylic. Allow it to cure for at least 15 minutes. Now prepare the guide tubes by cutting 21 pieces of polyamide with a razor blade. Begin this step by feeding all 21 guide tubes into the collector cannula at the bottom of the drive base. This will make sure that the tubes are all parallel to one another. If tubes in the bundle are too loose or tight, you can start with fewer tubes or add extra tubes as needed. Now remove each guide tube one at a time and feed it into one of the sleeves at the top of the drive. Pass the tube down through the gap it left behind in the bundle of tubes. Inspect the guide tubes for kinks or tight bends and replace as needed. Adjust each guide tube's position so it extends 1 to 2 millimeters from the top of the sleeve. Now add a small drop of thin cyanoacrylate glue to the bottom of the collector cannula. Be very careful not to let the glue flow into the guide tubes. Next, use a fresh razor blade to cut off the bundle of any excess tubing at the bottom of the collector cannula. Verify under a stereoscope that the tubes are neatly cut and flush with the cannula. Each electrode is advanced by its own microdrive, so we need to make 21 microdrives and then insert them into the plastic base. Each microdrive consists of a custom screw and a hollow support tube which are attached to each other with dental acrylic. The electrode will pass through the support tube. The screw features a non-threaded part with a small lip that is embedded in the dental acrylic and allows the screw to turn freely. In this way, as the screw is turned into the plastic base, it advances or retracts the electrode. The head of the screw is shaped like a half cylinder. Before we can make the microdrives, we need to make a screwdriver to turn our custom screws. Our makeshift screwdriver is constructed by taking a custom screw and completely grinding down the lip that surrounds the half-cylinder head. Insert the screw head out into a 5 cm long 15-gauge tube until it is fully encased. Now, crush the tube around the threads of the screw, securing it in the tube and preventing it from turning. Attach a mini pin vise to act as a handle and voila, a screwdriver. The microdrive is made by molding dental acrylic around the screw and the support tube. The molds we use are 3D printed plastic, just like the plastic base, and have holes in the bottom that keep the screw and the support post aligned as we pour the acrylic into the mold. First, we need to prepare the mold. Clear out the support tube hole using a 23-gauge needle. Clear out the screw hole and create threads using a tap. This is the same procedure we just used on the plastic base. Now the mold is ready to use to make microdrives. Line the mold with a Teflon-based lubricant to prevent the dental acrylic from sticking to the mold. Scuff the top 2 to 3 millimeters of a 14 millimeter long 23-gauge stainless steel support post with a grinding wheel so that it will be firmly secured in the dental acrylic. Insert the support post into the smaller hole of the mold so that the top of the post is above the top of the well. Apply a thin film of Teflon-based lubricant to a screw and insert it into the threaded hole until the threads are just below the bottom of the well. Now, mix up some dental acrylic and pour it into the mold. Make sure it gets into all the nooks and crannies. A needle can help dislodge air bubbles. Once the acrylic is hardened, you can remove the microdrive by backing out the screw. Do a strict quality check. There should be no cracks or bubbles in the acrylic. The post and screw should be parallel and unable to move sideways. The screw should turn smoothly but with no play. Any bad microdrives should be broken down and the parts reused. Repeat this process until you have 21 good microdrives. If your mold has multiple wells, then you can make the microdrives in batches to save time. Carefully align each microdrive with a pair of holes in the plastic base. Slip the microdrive support tube over the polyamide guide tube and into the metal sleeve while using the screwdriver to advance the microdrive screw. This can be tricky. Keep your eye on the center of the base to make sure that the guide tube does not get caught and buckle as the microdrive is lowered. Once all the microdrives are in place and fully lowered, a small amount of acrylic is dropped into the center of the drive to lock the bouquet of guide tubes in place. Allow the acrylic to cure for 15 minutes. Once the acrylic is dried, retract each microdrive about 3 mm. Create a top-down view schematic of the microdrives and give each microdrive a unique name or number. Now, looking in the stereoscope, flip the drive upside down and take a picture of the bottom of the collector cannula and guide tubes. Make a printout of the picture that can be used as a reference in the following steps. Next, with the drive upside down, insert a narrow polyamide carrier tube into each guide tube until it comes out the top of a microdrive. Note on the photograph which guide tube corresponds to which microdrive. The carrier tube will later protect and support the delicate electrode wire as it passes through the microdrive. Extend each carrier tube until it is 1 cm above the top of the microdrive support tube, and then glue the carrier tube to the support tube with 5-minute epoxy or thick cyanoacrylate glue. Be very careful with this step. If glue drips down the inside of the support tube, it can bind the support tube to the stationary guide tube, ruining that microdrive. This is the reason that we raise the microdrives before inserting the carrier tubes. Once all the carrier tubes are glued in place, fully lower the microdrives again and cut all the carrier tubes off flush at the bottom of the drive using a fresh razor blade. Next, cut the carrier tubes 1 to 2 mm above the top of the microdrive using sharp scissors. Finally, place the electrode interface board on top of the drive base and mount it with 2 screws. At this point, the drive array is ready to be loaded with electrodes. In our experiments, we typically use 4-channel microwire electrodes called tetrodes, but any type of electrode can be used. Fabrication of tetrodes, how to load them into the microdrives, and how to prepare the drive array for surgical implantation are covered in other Joe videos. This protocol can be followed directly or modified to meet your needs. For example, some researchers will require longer screws to record from deeper brain structures. Others may wish to design a drive that targets more than one brain location. The design can also be miniaturized for use in smaller animals like mice. With slightly more modification, motorized microdrives may be used which allow remote adjustment of the electrode positions.
We just showed you how to design and fabricate a microdrive array that can be implanted onto the head of a rat and allows us to record from large populations of neurons while the animal is freely moving. When doing this procedure, it's important to remember to carefully thread the holes in the plastic base so that the microdrive screws do not slip. Perform a rigorous quality check of the fabricated microdrives. Make sure the screw and the support tube are parallel and that the screw turns smoothly without play. Be careful when using glue or dental acrylic to not accidentally clog any of the tubing. Finally, remember that to complete the microdrive array and before doing the surgery, you will have to fabricate tetrodes and load those into the drive. This is covered in another Joe video article. So that's it. Thank you for watching and good luck with your experiments.